Hello everyone, welcome back to the channel. You are watching Build AI with Sandeep. In today's video, we will understand the three very important concepts of the transformer architecture, that is self-attention, multi-head self-attention and the skip connections. These concepts are the backbone of the ChatGPT, BERT and many modern AI models. I will explain them in a very clear way so that you all can understand easily with visuals. This time I am coming with very good visuals. I found a site draw.io where I can draw the architecture, where I can draw the diagrams that can represent easily, that can help us to easily understand the transformer architecture. So let's quickly start our today's video. So what is self-attention? So first thing first, what is self-attention? If you want to understand what is self-attention. So self-attention is a smart way that finds how important each word is with respect to every other word in the same sentence. Let me write the definition first. Each word is with respect to every other word, including itself, in the same sentence. Same sentence. So this is the proper definition of self-attention. You can understand by with example. So let me give you an example. The cat is sat on the mat. Here, imagine we are just focusing on the word set. So what do you think that set is important to which words in the sentence? So the first one is cat. Who sat the first word, and the second word. What do you all thinking? All are thinking that what will be the second word? That is more important to the word set. So I guess you all say mat. Where set? Where cat set? Okay. So language models, how language model are understanding the relationship that set is more important to the cat and mat. So that is why we are saying that self attention is the heart of the transformer architecture, because the everything, the magic is happening inside the self attention. Who can understand this relationship, that okay, set word is more important, more relate to the word cat and mat in the same sentence. And why we are saying attention self, why we are adding self to the attention, because we are looking word inside the same sentence including itself. Okay. And so this is the self attention basically. Now now how self attention can do this, how self attention can understand the relationship, grammar and language understanding, how it can be done. So let's start with this flow. So I hope this flow will help a lot in understanding the transformer architecture. So I pick this sentence: cat drink milk. Now here we can again understand that drink is more important to cat and milk. Okay. So for example purpose, the process starts with input embeddings. Then so this is so we start with this here, then we add positional embedding, then after that, that will be the input for attention, self attention. Okay, and we will move like this using the same architecture. So this is our input sentence. This is our input sentence. So I said in my, I explained in my last video that sentence will be tokenized first, and we assign unique token IDs to each word. Okay, so we assign 11 to the word cat, 27 to the drink. So these are our token IDs. Then we create input embeddings for each word. So for this 11 token ID, we create a vector of size 3. In original transformer research paper, the embedding size if is 512. Okay, but since 512 is a large number, so for teaching purpose, I pick 3 size vector. Okay, so basically for each word we create embeddings are nothing but a vector representation for each word so that machine can understand better. Okay, we created vectors, vector embedding for all the 3 words. After that we will provide positional embeddings. We will add positional embeddings to our input embeddings to provide the information of the position. And in my last video, I explained positional embedding, that we are using sine and cosine formula to create these vectors, these values inside the vectors. Okay, and sine and cosine are smooth and repetitive. That's why we use sine and cosine to create these positional embeddings. We add up these positional embeddings to our input embedding that gives us our input for self attention. Input for self attention. So these 3 vectors are our input for self attention. Now, everything is happening in parallel till now. You, I guess you don't have any doubt till now. Now coming to the self attention part. So what is happening inside this flow? Each vector went to the self attention. For example, this vector is going inside this vector is also, this vector is also, and there are 2 self attentions I am using. But for now we are let's first understand what is happening inside this self attention block, and so let's start this. Okay, so these 3 input self attention, these 3 inputs for our self attention block. So now the process goes here. So we will, so self attention understand grammar, understand the relationship between the words. How it can be done? It can be done by creating 3 vectors. Okay, 3 vectors, query key value. What is this? Let me again tell you that Q is for query, Q is for query, K is for key, and V for value. Okay, and how we will create this query key value? We will multiply our input embeddings with the learnable weights of the query vector. Okay, so we have 3 vectors of size 3. So we will create a matrix. We can create a matrix of 3 vectors. We will stack up all the vectors like this, and that will give us the matrix 3 into 3. So after that, what we will do is we will create again, we will create a 3 into 3 matrix, weight matrix, that have random weights that can be learned during the back propagation. Okay, so after multiplying this, that will give us 3 into 3 vector, 3 into 3 matrix. So we will, this is our QW or WQ. Okay, so that will give again 3 into 3 vector, and those three set of three set of vectors having size 3. So for each word we we will get 3 query vector. I hope you understand. that for each vector we will get 3 query vector by multiplying 3 into 3 weight matrix of random values that are learnable parameters that will will be learned during the back propagation, that will be learned during the training. We can also use training. Similarly, we have three input embeddings. We will multiply these 3 into 3 matrix with WK. Again, this is again a random weight matrix of key. Okay, having three set of vectors having random values that we can say, that we will say weights. Okay, so again we will get key vector. Again we will get key, three vectors for each word that represent each word, and similarly we will multiply WV. Okay, with the input embeddings that again give us three set of vectors having size 3. Okay, so in this way we will get our query key value vector for each word, now now the formula is softmax of query key t. Okay, so first we will multiply query vector, query matrix with the key matrix, but this T is transpose. This T is transpose. Okay, so how do we transpose? So in the values you can see I just stack up vertically all the query vectors, 0.15, 0.25, 0.18. So 0.15 is here, 0.25 is here, 0.18 is here. But for the key matrix, what I do is I transpose the values. So 0.10 is here. Okay, so then 0.15 should be here in if in case of query matrix, but in transpose we will interchange the column and rows. Okay, so 0.15 does not come here, but it will come here. Okay, so 0.12 similarly here. So this is transposed. Okay, so after multiplying this query key transpose, we will get this matrix. Okay, so after doing this, we will apply softmax function on the query key transpose. There is also one more thing we can do. We can divide by dk, and this is the dimension. In our case, each vector is of size 3. So, in original research paper, there is division by root dk. In the last video, I explained why we divide by dk to scale down our dot product values, because if the dot product gives us bigger values, then we apply softmax. Then the output of softmax will be sharp. Many values are closer to 1 and many values are closer to 0. So due to this reason, to scale down the values after the dot product, we are dividing by root dk. But in our case, the data set is not too large, so that's why I did not divide by dk. Okay, so how do we apply softmax? What softmax function can do? So I already write the formula of the softmax. Okay, so this is the softmax function, j equal 1 to n e to power x g, and this is I. This is I. Okay, so let's take example so that we can easily understand. So for row 1, so let's pick row 1 of this output matrix, 0.05 point this. So our x1, x2, x3 are these values. So this I is nothing but 1, 2, 3. I is 1, 1, 2, 3, like this. Okay, so we have x1, x2, x3, and we are going to find exponent of each word of each x1, x2, x3. So we will do the exponent here, then we add up all the exponent to make this sigma j equal 1 to n e to power xj. So this is summation, is basically to sum up all the exponent values, and that will give us 3.191. Now The last step is now we have separate z xi values, and we have the summation of all the exponents. Then we divide. Softmax of x1 is what? 1.051 divided by summation of this value. Okay, so we will find softmax of each values uh, every place, and that will give us these three values. So then we put the values right here, and similarly we can do for other values also. So this completes our softmax query key value, and that is representing by this matrix. Now the last step of this is multiplying by v value. V matrix. Okay, so V matrix is again nothing but a matrix having values, having random values, random weight values. Okay, so after multiplying, we are doing matrix multiplication that will give us the final contextual representation of each word, and it is the final output of the self attention. Okay, so you guys can think why we did all this to understand the grammar, to understand the contextual information, the relationship between each word. We are doing query, we are using query key value. So in the last video, I gave some context about the query key value, but again, I'm telling that we are taking each word. Query represent what we are looking for, which word. Okay, so in this word, so in this, the first row that represent cat. So we are querying cat word inside each keys. Keys what? Cat, drink, milk. So again, each word is representing by this row. We did transpose. So cat is looking for in all the keys, in including itself. Cat is also here. So we are querying cat inside all the keys that we have inside the sentence. Okay, cat drink milk. So query karega. So it will do query. After that, it will return a value. Then we apply softmax, and this softmax query kt multiplied by value vector. So that eventually gives us the contextual representation of each word. Okay, now this vector is representing cat, this is drink, and this is milk. Okay, and this is the final output of the self attention. Now we understood only one self attention. But in original research paper, there are multiple self-attention used, and after combining all the self-attentions, we will get what? Multi-head self-attention. Multi-head self-attention. So we only look at one head, one self-attention head. But if we can do the same operations for multiple times, and after concatenating the results of all the self attentions, then we can say that multi-head self attention. Okay, so why we are using multi-head self attention? Because see, every sentence there are many times. For example, let's look at the sentence. I went to bank to deposit money. To deposit money. So here the word bank. So bank is financial bank where we actually went to deposit money. But there is another meaning of bank is riverside. Riverside. Another example we can take, the chicken is ready to eat. So so the sentence the chicken is ready to eat have two different meaning. Chicken is ready to eat or someone else is ready to eat chicken. There are two perspective of the same sentence. So So to make our transformer architecture, to make our large LLM model, to understand the different perspective of the same sentence, we use multi-head self-attention. In many cases, one self-attention is only learning grammar. Other self-attention is learning some other relationship between the words. Okay, in third self-attention, maybe that self attention is learning some other relationship in the language. So that's why we are using multiple self attentions, and after concatenating all the self attention, multi head self attention will be made. Okay. Now now see, till now our every operations gives us output of size of vector size 3. Okay, so now here also this self attention gives us this output, this self attention gives us this output, this output matrix. Okay, so for each word everything is working in parallel. Now for drink word, only for drink word, I'm picking how so how can we combine the results of multiple self attention. So for drink word, this vector we got from this first self attention, and we got this vector from second self attention. So in transformer architecture, what we can do is we can concatenate the two vectors horizontally. Okay, so like this, we concatenate first, need first, and then we apply a linear layer to compress the vector back to size 3. So I write I write it down, the definition of linear layer. The linear layer after multi-head attention is purely linear transformation. Make sure don't confuse with the neural networks, deep learning neural network. This is not a neural network. This is not a neural network. This is a linear layer. Here, only multiplying by weights, adding and bias operation are happening, but no non-linear learning. I'm saying non-linear learning means we are not applying any activation function. We are just multiplying with weight matrix again. Okay, and adding a bias. So is purely linear transformation, it including bias but does not use any activation function. Once we compress and mix the attention head outputs, the real non-linear learning happens in the feed forward network using ReLU. So, so it is mentioning that this feed forward network, uh, so, so I will explain this feed forward network in the next video. But right now, you just understand that there is no activation function, but a linear transformation. For example, we have 1 into 6 row. We can describe any matrix using describe the matrix size using this notation. And the first one is this is number of rows and this is number of columns. Okay. So if we want to get an output matrix of size 3, 1 into 3, then how would we get that? So in matrix operations, you have some idea about the matrix operation, that 1 into 6 matrix is multiplied with 6 into 3 matrix, and this is weight matrix having learnable parameters. Weight matrix having learnable parameters. So this will cancel down and the output matrix will be 1 into 3, and that is this vector. So this is basically a vector of one row and having 3 columns. Okay, so for drink word, we will get this vector, this attention vector, and this is the final multi self attention output. Similarly, for cat word and milk word, again we will do the same operations, and we will get two other vectors of size 3 after that. So now till now we understand what is the self attention. Self attention is a smart way to understand, smart way to find how important every word is with respect to each other word in the same sentence, including itself. So this is self-attention. How self-attention can understand grammar and contextual meaning? By creating 3 query key value vectors. Okay, and after that we apply softmax function and multiply by value matrix, and we will get the output of the self-attention. Okay, after concatenating, taking multiple self-attention output and concatenating, then we will get multi-head self-attention that captures different perspective of the same sentence. Okay, this is the main reason behind reason behind using multi-head self-attention. Okay, and after that we will apply a linear layer to compress back to the same size as the input of self-attention. Okay, now coming to the our last concepts that we are supposed to learn today, that is skip connections. Okay, so you can see this line. You can see this is the input. This is the input of self-attention, and we are adding up the same input to the output of the self-attention. Why we are doing this? What is the need of doing this? So let me tell you the reason behind using skip connections, because because output of multi-head self-attention is the new information we are getting. But after doing all the operations, we did multiple mathematical operations, so there are chances that our model might forget the original information. So we are giving the input of multi-head self-attention again to the output, because we want to preserve the original information, because in future also there are multiple operations will be happening, will be done. We will do there is add and normalization. So add part we are discussing right now, that we are adding the input of self attention again to the output of the multi-head self attention. Okay, then we will do feed forward operation. After that there is again add and normalization. So multiple operations can be done. So we want to preserve the original information. That is why we are using skip connection, that makes our training faster, that preserve original information of the input. So these are the reasons using skip connections. Okay, so when we add skip connection, when we add the original input vectors, that will give us these three vectors that is representing each word. Okay, and after that there is a concept called layer normalization. So we will understand the layer normalization and the feed forward operation in our next video. So now we understand what is we understand the three concepts, the three major concepts, and the self attention is the very important concept, very important concept, that is, that is the main reason behind large language models, generating next token, understanding more grammar. Okay, so I hope you understand flow chart using this flow chart, and you understand all the mathematics and the operations that are happening inside the self attention. So if you like this video, please do hit like, subscribe, and comment if you have any questions, if you want more videos for any specific topic. So thank you so much for watching my video.